Hello, my name is Alexey Fedorov, and I'm going to tell you about our experience of using C3D solvers in the 3D module of the Nanocad application. It's a product of Nanosoft company. It's a CAD application, primarily targeted for Russian market. It has a familiar AutoCAD-like interface, powerful drafting and design tools, native DWG compatibility, an open API for C++ and .NET, and it has a built-in 3D module currently working on C3D modeling core. This is a typical screenshot of Nanocad. In this particular picture, a 3D modeling sample is demonstrated. Several years ago, Magma Computer, the company I work for, started connecting a 2D constraint solver to Nanocad. The task came from Nanosoft company. Initially, it was 2D solver from Ledos company. Then we did the same job for the 2D constraint solver from C3D. And finally, we've attached its 3D constraint solver. Currently, solvers are connected to Nanocad in three ways: a DWG model, a direct connection of 2D solver, and direct connection of 3D solver. Now let's look at these ways a bit closer. The first one is a DWG model. It consists of 4 layers. The first one is the main application itself. The next is the layer of the ODA SDK. Then there is a specific 2D constraint solver. And the last one layer is the 2D solver itself. It's designed so every layer may interact with 2 layers only, the one above and the one below. It's displayed with blue arrows here. A constraint solver cannot interact with the main application. On the whole, it causes a set of functionality limitations and performance issues. In order to avoid some of them, Nanocad directly interacts with all mentioned layers. It's displayed with pink arrows. The next attachment scheme is a direct connection of 2D solver. In this case, the DWG layer is completely excluded. Nanocad uses such type of connection for solving flat parametric sketches in standard 3D parts, objects in database, such as nuts, flanges, and so on. In this model, a 2D constraint solver is connected through a small gate module, which is implemented as a C++ library. Nanocad may almost directly interact with the solver. The last connection scheme is a direct connection of a 3D constraint solver. Nanocad uses this model for evaluation of constraints between 3D parts and assemblies. Now let's look at the 2D constraint solving process itself. In a DWG model, it may be represented by 3 stages. The first one is an event telling us about changes in object's geometry. The stage 2, identifying the type of such changes. And the third stage is constraint system solving in a certain way. Simple shifting of an object, simple rotation of an object, moving a vertex of an object, and general solving. A question may arise here, why we need to determine a type of geometry changes. It seems it's something that should be known by definition. If a user moves the whole line segment, it should be a simple shifting mode. If he moves the ending of a curve, it should be a vertex movement mode. However, in a DWG solver connection model, changes are initiated on the top level, a level of application. But a solver is isolated from the application by abstract and common purpose interfaces. Now I'd like to demonstrate just mentioned calculation modes. The first one is the simple shifting of an object. On this screen, the most left green line is about to be shifted upward. Here is the result of calculation, sort of animation. We may see that the shifted line is at the user-desired placement. Other objects retained their relative position, but got a slight rotation. But this isn't an error, because the rotation of objects isn't limited. Now let's look how simple rotation of an object is processed. The blue line at the bottom is about to be turned to a position of the yellow line. So its lower point must remain fixed. Let's look at the result. Again, sort of animation. And we may see that the line has been rotated correctly, and the rest of the sketch has been properly repositioned too. However, there are questions to the left line with the ending without any constraints. We may see that the line has been rotated so that its length remains the same, and as if an angle with the adjacent vertical line was fixed. Another possible way to recalculate for this line would be to keep the left ending on its place. Nevertheless, the constraint system stays in a correct state that satisfies all existing constraints. If a user requires more predictable behavior of calculation, he should provide additional constraints. This is the most helpful advice for such cases. On the next screen, the ending vertex of the green spline is about to be moved to the pointed place. At the same ending, there is a smooth constraint that's set between the spline and the red line. Smooth means G0, G1, and G2 curves connection. And here is the result of calculation. To unknown reason, the solver has rejected the target position and has calculated the system for another point, this one. Additionally, the spline got a noticeable excessive curvature, though all constraints here are in a solved state. I guess there is a bug in gate modules for a solver, and this is the issue for further explorations. Finally, let's look at the general type of constraint solving. Its purpose is to bring a constraint system to a state when all constraints are satisfied. Such way is suitable, for instance, for the case when parametric constraint values are changed. In our sample, a user has entered new values for all three parameters of the sketch, values for radius, distance, and an angle. Here is the result. Three pointed geometry entities have retained their positions. We may see that the geometry of the sketch looks similarly to the initial one, and objects' relative positions have also been kept. Everything looks fine. Now, some words about the direct type of connection of 2D constraint solver to Nanocad. Such model is used for calculation of 3D standard parametric paths, templates for which are stored in a database. On this particular screen, we may see a model of the node. The image in the left bottom corner is the 3D modeling history tree. The sketch with constraints in the center of the slide participates in this model calculation. The important point here is that the sketch must be fully constrained. Such condition eliminates all issues relating to calculations of under-constrained systems. Today, the 2D solver is successfully connected to the Nanocad application and carries out all required tasks. However, things weren't so fine when we started working with it. Some issues took place and had to be fixed. Some of them were significant, were simple but significant. Fixing others took more than a year. The current slide has a list of such solved issues, and I'd like to talk a bit about them. Let's start from the one that was successfully solved with an assistance of the C3D Labs team, but without changes in the solver's API. Some consultations took place. Then we managed to implement a symmetry constraint for C3D Solver. The point is that the C3D Solver requires a programmer to specify every aspect of symmetry explicitly. The symmetry for points, arcs, ellipses. There is a specific processing for symmetry even between boundary lines and their unbounded versions. Looks quite complex, but finally it works. Rigid sets in 2D constraint system. Initially, 2D Solver in C3D didn't have API to create such objects. A rigid set is a set of geometric primitives that are fixed relatively to each other. In a DWG model, such sets are required for applying constraints between instances of block references. On this current picture, you may see two rectangles. Some constraints are applied to them. In this case, 4 lines in every rectangle are composed into a single rigid set. So we have 2 of them. C3D Labs implemented the required functionality in response to our request. These 3 functions were added to the API of the solver. Lots of work was done for implementation of a smooth constraint. Smooth in terms of DWG is a composite limitation representing a G0, G1, G2 connection. In other words, equality for point coordinates, tangents, and curvature. The scheme on the screen contains the set of implicit constraints and their relations required for representing such a complex object. During our discussions with C3D team, it was decided to implement API suitable to calculate the same structure of limitations as the displayed one. Names of structures and objects are slightly different, however, their meaning is similar to the ones in the DWG model. The last significant improvement in the API of 2D Solver relates to the generated values of parametric constraints. It's irreplaceable in case when you need to create different implementations of 3D parts using the same 3D model. The NAT object displayed on the left has 2 implementation. The top one has chamfers, shown in green color, and the bottom implementation doesn't have them. The sample is provided only for understanding the discussing topic. Of course, real NATs always have chamfers. With new improvements in a solver, we may inform the system that dimensions N4 and D6 in this case may degenerate to 0. Then we put such values into parameters, I mean zeros, and execute a general solving. The last part of my presentation, I'd like to tell you about how we've connected a 3D solver. Currently, an Nanocad application offers a user 6 types of 3D constraints: a fixation, a mating, an angular constraint, an insert, tangent, and a symmetry. This set provides the minimum necessary constraint types for 3D assemblies modeling. The table has information about types of object geometry references that may be put together for every type of constraint. The mating constraint is the most functional one. It may be used for mating any pair of such primitives as a point, line, and a plane. There are 9 combinations to take into account in order of constraining objects. I mean that, for example, a line-plane and plane-line relations are different in this case. Talking about the tangent constraint, not all possible combinations are currently valid. For example, a cylinder surface cannot be used in a pair with the conical or spherical one. Moreover, a tangency between two cylindrical surfaces doesn't mean that their axes will be parallel. Such limitations must be added by users explicitly. Some items of 3D body may participate in different 3D constraint relations. The most representative one is a circular edge. It may be represented as a point, the center of an arc, as a line, the axis of an arc, and as a plane that the arc lays in. Nanocad interacts with the C3D Solver directly using the scheme that's displayed on the current slide. The initial step is to collect a set of altered 3D bodies. Then, when the update event comes, the calculation of 3D constraints begins. It carries out into two stages. First, a fixation is applied to all 3D parts that were moved. Then Nanocad queries a 3D solver to calculate constraint system. If it's successful, the result is applied to a model. If the stage fails, a general calculation of 3D constraints system is applied. If this stage fails too, Nanocad collects states of every 3D constraint using the information provided by the solver. Such states as solved, conflicting, excessive, and so on. Then this information is reported to a user. Here is an example of such case. There are three constraints. They are applied to a couple of cylinders. Two of constraints are inconsistent. The angle constraint and the cylinder's axis mating. In this sample, a user has just entered new value for an angle. The valid value is 0, but now it's 155, and it conflicts with the existing mate constraint. The effect of inconsistent is visible to a user, so he may fix corresponding errors. So that's all for technical details. Let's make a little summary relating to C3D solvers. 2D version supports all 2D constraints required for DWG format, predictably solves fully constrained 2D sketches, has acceptable calculation speed, has better functioning and performance in direct interaction. 3D version of the solver has a user-friendly, understandable API. It's robust and qualitative, no issues found so far. And I should state that both solvers don't require special license. The general one enables all of them. I hope my story was interesting to you. We appreciate C3D Labs for their professional assistance. I believe the job they've done for us made a positive contribution to the C3D product itself. That's it. Thank you for your attention.